Hi there, welcome to my videos on elementary differential equation. This is video number 7 for chapter 8, where the topic is Fourier series. We have observed and commented in previous videos this interesting property of the Fourier series. In the case where the function is an even or odd function, the Fourier series takes special forms. So let's formulate this and take advantage of this property. Let's define an even and odd function first. So a function is called even and if it has the following property, that is, if you make the x negative, you do not change the function value. So f of negative x equal to f of x. And you can see this in the graph of the function. So the graph of function will be symmetric about the y-axis. That is, if you plot it on the paper and you fold it along the y-axis, and then the left and right would perfectly match each other. And examples of an even function would be a constant function, f of x equal 1 or any constant. And another one is the cosine function, cosine nx for any integer n. Now look at the counterpart of that for an odd function. So for an odd function, if you make the x negative, and the function will return a negative value. Therefore, f of negative x will equal negative f of x. If you want to see this property in the graph of the function, then you see that it is symmetric about the origin. That is, if you have the graph there and you put a pin at the origin and you rotate the graph 180 degrees and it matches the original one. Okay, so typical examples in our setting, that is the study of Fourier series, would be the sine function, sine of nx for any integer n. This is an odd function. Okay, let's collect some properties. We have commented on all about that. So first is product of even and odd function. So if you have two even functions, then the product of them is also an even function. And before I go on with the other two, we could think like an even function is the positive sign, the plus sign in front of a number, and an odd function is like having a negative sign, a minus sign in front of it. And then positive times positive, even times even is even. Okay, and then the next property, if you have two odd functions, then the product of them becomes even. That is, if you have a negative sign in front of both functions, and then the product of them will have a positive sign. And then the last one will be the product of an even and an odd function, like with a plus sign and with a minus sign. And in the end, you will get a function which is odd. All these can be quickly proved by using the definition with one line, so I will not go into that detail. Now, the next two properties will be useful in computing Fourier series. So integration of an odd function over an interval around the origin, say from negative L to L, would be 0. Because it's an odd function, it's symmetric about the origin, then the part on negative L to 0 matches the part on the integral of from 0 to L, but with an opposite sign, and adding them up, you get 0. Okay. And then the last property is the integration of an even function over such an interval around the origin. Then from negative L to 0 and from 0 to L will give you exactly the same value, even with the same sign. Therefore, you can just integrate from 0 to L and then multiply the result by 2. Okay, let's collect a couple more observations we have made. If f is an even function, we have observed that the Fourier series will not have sine functions, which means it will only have cosine functions and the constant term. On the other hand, if f of x is an odd function, then the Fourier series will not have the cosine terms, meaning that the Fourier series will only have the sine functions. We could feel that this observation fits the instinct. So the instinct says you cannot represent an odd function with the sum of an even functions, because if you sum up all bunch of even functions, the function will be even and it can never represent it an odd function, and vice versa. And we also observe that the formula for the Fourier coefficient in these two cases can be simplified, and you only need to integrate over half of the period. Okay, so let's summarize these formulas. And these will be called Fourier sine series or Fourier cosine series. Okay, so now if fx is an even function, periodic, with period 2L, then it has a Fourier cosine series for even function, and we can write it like that and only have the constant term and the cosine term. And the Fourier coefficients an can be computed by integrating half of the interval from 0 to L, for example, and then multiply it with the 2. And correspondingly, for the other case, where f is an odd function, periodic, with period 2L, then it has a Fourier sine series. Okay, so odd function will have sine series because sine functions are odd functions. Okay. And then it would take this form. You only have the term of sines and only have the coefficients bn. And here the bn, again, the formula can be a bit simplified. You would integrate from 0 to L, and then you will multiply it by 2. Okay, so all these are nothing new. We actually have observed all of these already. And now, what is more interesting from all these observations will be the next thing we'll be talking about. So we will utilize these properties to represent functions that are not periodic in a specific way. Okay, so here we talk about half-range expansion. So let's say I have a function fx. It is only defined on some interval from 0 to L. It's a generic interval. You can have interval from A to B and then move it to be from 0 and L. Okay, and then if that is the case, then we can extend or expand these two terms we will use interchangeably. You can expand the domain into the whole real line by periodic expansion. So there are two ways of doing this. Let's look at the first way. First way will be I take the function fx defined on the interval from 0 to L. I first extend this interval into an interval around the origin from negative L to L in such a way that f becomes an even function. That is, f of negative x equal to f of x. This means you can make it to be on the negative L to 0 on that interval to be symmetric about the y-axis. Okay, you can take the part from 0 to L, like flip it and over and put it on negative L to 0. Okay, then you have a function defined on the interval from negative L to L with the length 2L. Then I would take the image there, like make a stencil, and then copy it into a periodic function with period 2L. So I copy it to the right over a period 2L, keep going, and then same to the left from negative L to negative 3L, and so on and so forth. And later we'll take an example, and this will become clearer. A second way of expansion would be, it happens right here. When we extend the function fx onto the interval negative L to L, I can make it in a way such that f is an odd function right there. That is, f of negative x equal to f of a negative f of x. Okay, which means you can extend it so it's symmetric about the origin. And then you extend it further into a periodic function on the whole line, whole real line, with period 2L. Okay, so these are called even, odd, periodic extensions of f, or since you use only the half range of the periodic function, it's also called a half range expansion or extension. And once you have done the expansions, then you have a periodic function, might be even or odd, and which you can write out the Fourier sine series or Fourier cosine series correspondingly. Okay, let's take an example. So let's have a function f of x equals x, just to be simple, to get the idea, and that is defined on the interval from 0 to L. You can even think L equals 1. Okay, and then you are asked to sketch 3 periods of the even and odd function of f, and then compute the corresponding Fourier sine or cosine series. Okay, so let's take the case L equals 1, and then we can use a graphic tool like MATLAB to draw these functions. Okay, so the graphs are given here, but let me take some time to explain how these were given, were computed. Okay, so let's say L equals 1, and I want to have an even extension. So how do I do that? So let's draw an interval, let's say 0 and 1. Okay, y-axis, and let's say this is 1. Okay, so on the interval from 0 to 1, fx equals x, so it's a straight line with slope 1. It goes up like that. Okay, now the first step is to make it into an even function. Let's do it in the red from negative 1 to 1. So an even function, the graph will be symmetric about the y-axis. So I will take this part and then copy it like in the mirroring fashion. So it will be from here with the slope negative 1 coming down. Okay, now I see that on the interval from negative 1 to 1, this function is just like a valley going down and then back up. Then I can take like a stencil of this, like make a copy of it, and then let's say, let me do it in blue. I will do it from the interval from 1 to 3. So I'll copy this and then repeat it. So I will come down with the slope negative 1 and then come up with slope 1. Okay, sorry, this hand drawing isn't so pretty. And then I can do the same thing here, negative 2. Negative 3. I copy the same in the same way, so it's down and comes up. Okay, so this is exactly what is drawn over there in the even extension. And now let's do the odd extension. Let's mess up this graph. Let's say I'm going to do it with the yellow color. So how do I make an odd extension from negative 1 to 1? Well, the extension will be symmetric about the origin, so it will actually come down here, right? So I will have this extension come all the way to here. So actually, it's the function on the interval from negative 1 to 1 will be just a straight line with slope 1 going up. Okay, and then we're going to make a stencil of it and copy it to the left and to the right. So let's consider first on the interval from -1 to 3. I will just have to copy this slope 1 line over there, and then we immediately see that at x equal 1, it will have a discontinuity, have a jump here, and it will go all the way there, so it will be like this. And then on the left, it will be similar. At -1, there will be a discontinuity. And then from -3 to -1, I'll have a line with the slope 1. And it repeats. It's periodic. Okay, so this graph is a bit messy, but it shows you how different these two functions will be. Okay. And also, it's a bit clearer with the scale of the y-axis. Here is a bit hidden. See, the y-axis here is from 0 to 1, but then for the odd extension is from -1 to 1. Okay, now let's compute Fourier series. Let's consider the odd extension. And we see that the shape, they resemble sawtooth, so therefore these are called sawtooth waves. And since it's an odd function, we'll have Fourier sine series. Okay, let's put up the formula to compute the coefficients, bn's. Bn will be, this will be the formula, and f of x is x. And we see that we need to integrate x times sine. We can use the tabular method, which we have talked about in a couple of videos. Let's try to go through that quickly here as a practice. So let's set up our tableau. So I have function x here on the column A, and sine of n pi x over L as the second column. And then this will be the diagonal product on the last one. So I differentiate this, I get 1, I differentiate it again, I get 0, so I stop. And then I integrate the sine, which gives us negative cosine. Then have negative constant L over m pi. I'll get cosine m pi x over L. And then I integrate that one more time, and I'll pick up the constant again, so I get L square, m pi square, and I have the sine m pi x over L. Okay, and let's find the diagonal product. So the term here would be the product of this times that. Okay, let's write this out. I'll get negative x times L over m pi, and then cosine m pi x over L. And then for this term, it will be this times that, and it will carry a negative term, and it will cancel that negative sign, so we'll just have L over m pi square of sine m pi x over L. Okay, and then we stop here and we collect the terms, which will be this one plus that one. And these two are almost common factors, but with something else in it. So what I did in this computation was I take this as a common factor, and I multiply this term with the m pi over L. And look, that's what we did here. Okay, so the sine term is here, and the cosine term with the x is here, and multiply it that way. Okay, then we can evaluate this expression at x equals 0 to L. And we first see that at x equals 0, sine is 0, and this is 0, so it's gone. So we just need to put it to be x equal L. And at L, this is sine m pi, which is 0. So we just have this term. So that will be, when x is L, and I have an m pi here, which cancels one of this n pi. So we just get 1 n pi, and this L cancels one of this L, so I just get 2 times L. And then I will end with the cosine n pi, which is negative 1 to the power n, and pick up the negative sign here, so it would be negative 1 to the power n plus 1 for n equal 1 to 3. Okay, then we can write out the odd extension, which is a Fourier sine series. It will equal to that. We take out 2L over pi as the constant outside. And we can write out a few terms of it. And when n equals 1, this becomes an even function. That becomes 1. So I get sine pi x over L with a positive sign. And then each other sign will have each other terms will have alternating signs, because here is negative 1 to the power n plus 1. Therefore, when n is 2, we get a negative term here. And then when n is 3, we get a positive term. And then when n is 4, we get again a negative term with 4 here and the 4 here, which is here, and so on and so forth. So this is just to give you an idea to look at each term, how they look like. And also you can plot partial sums. Okay, so now let's look at the even extension. We see that these even extensions are like triangles, so they're called triangle waves. And it will have a Fourier cosine series. Let's compute the coefficients. So let's compute A0 separately. And this will give us 2 over L, integral from 0 to L of the function, which is x. Okay, and this on the interval from 0 to L, it's x. It's just to compute the area under a triangle of length L. So it's L squared over 2, and you easily get L. And then let's compute an. We see that the formula is this, and this is fx. We see we have to compute the integral of x times cosine, which can be quickly done with the tabular method. So we went through the detail for the case of the sine, and the cosine is in a similar way. So let's skip the detail and get to the terms, and we'll have 2 terms. They are like that. We collect it, and then it's evaluated from x equals 0 to L. Okay, let's set in the limit. So first we observe that the term sine here, m pi x, when x is 0, the term is 0. When x is L, you get a sine of m pi, which is 0. So this term contributes nothing. You just need to evaluate this term. So I collect all the constants here, over here, and this term will be set x equal to L. Then I get cosine m pi, which I put here. And then the lower bound is x0. Cosine 0 is 1, so I get that. And then we can put in the nice expression of cosine m pi, which is negative 1 to the power n, in here. And that is for n equal to 1 to 3, and so on and so forth. Okay, so this expression here actually gives us a bunch of zeros. We see that when n is an even number, negative 1 to an even number is 1. 1 minus 1 is 0, so all the an's are 0 for n even. And then when n is odd, you get negative 1 with negative 1 gives you negative 2. Put it here, you get negative 4. So you have this expression for n odd. Okay, now we can write out the Fourier series f even for the even extension. So the constant term a naught over 2 here, and everything here has a negative sign, so I put a negative sign here, summing over n odd of this term times the cosine functions. Okay, so we can write out several terms of it. We can easily do that and put n equal 1. We get this term. and the next is n equals 3. So we take out 4l over pi square outside. Okay, so we basically have 1 over n squared cosine n pi x over l. So setting n is 3, I get 1 over 3 squared, 3 pi. And then n is 5, I get 5 and a 5. So here's 5 squared. Here's n equals 7, I get 7 here, and then 7 squared down here. We conclude this discussion with some plots of the odd and even extension and the partial sum of the Fourier sine and cosine series. Okay, so they're plotted side by side, and this column is for the odd extension, and this is for the even extension. And this is partial sum y1, taking one term and taking two terms, and then 3 and 4. So if you take one term, and for the odd extension, you just get this sine function, and then for the even extension, you get a constant. So that seems like a pretty bad approximation. And then if you take one more term, this odd extension try to do a bit better job, and the even extension is a cosine function, a negative cosine function, plus some constant. Okay, and then taking 3 terms, it's trying to approximate it even better, but seems like it's having trouble here when the function has a jump. And then for the even extension, taking 3 terms, it approximates a lot better. Okay, let's take one more term, and then you see the function try to oscillate a bit more to approximate this discontinuous periodic function with discontinuity. Well, it looks a bit better, but still we see quite a bit of difference here. And then for the even extension, visually it looks like a pretty good approximation. So it will be probably clearer by plotting the arrows. Okay, so here are the arrows of the even and odd extension, just the arrows of the function in the previous graph. And I want to call your attention to the scale of the arrow. Okay, so taking one term in the partial sum for the odd extension, this is the arrow. Look, the arrow is from -1 to 1. Okay, and then for the even extension, the arrow is from -5 to 5. This is quite big. Okay, taking 2 terms, that's the arrow. This part gets smaller, but this part where the function has a jump, it's pretty big. It has peaks. We have observed such behaviors already. Okay, and it's from -1 to 1 as its scale. Okay, and for the even extension, this is the arrow. We observe also some peaks where the function has a kink, but the scale of this whole thing is from -0.1 to 0.1. This is just 1/10 of this scale, so much, much smaller. And then taking one more term, and that is the plot of the arrow. So in here it becomes smaller, but it still contains these peaks. And then here is for the even extension. It's the arrows like that, and look at the scale. It's 0.04. And one more term, and here you are kind of stuck with from -1 to 1 because the peak here is so high. But for the even extension, and see that is much smaller. Okay, so it's not really surprising, isn't it, why this one behaves so poorly? That is because you have a discontinuity and in the original function, and you are trying to represent a discontinuous function with a series of sine cosine functions which are continuous. You would expect at the point of discontinuity it might not do such a good job. Okay, so we'll discuss more about convergence in the future videos. So let's end this one here today. And I hope you enjoyed it, and I'll see you next time for more discussions.